So for lesson 4.2, we're still looking at the derivatives of the sine and cosine functions. So just to kind of recall here from the last lesson from 4.1, and actually I would have your 4.1 note out in front of you if you can, or again, if you're watching on your own, just maybe have it up on the screen to pause the video at times when I say to go relate back to those graphs. So we have the sine function here is in purple, right? Starting at 0, going up to 1, back to 0, down to 1. And our kind of key points for the radian or degrees are happening, let's say, to the right is 0 at pi over 2 or 90 degrees, then at pi 180, 3 pi over 2, and then at 2 pi. And to the left of 0, which isn't on the screen here, is the same thing but negative. So negative pi over 2, which is negative 90 degrees, negative pi, negative 3 pi over 2, which is again negative 270 degrees, and negative 2 pi, which is take pi, which is 180, and double it, and you get 360, so negative 360. And the derivative of that we learned in the last lesson is just simply the cos curve. So here's the cos curve here in whatever you want to call that, kind of browny maroon color. Then we looked at here, just need to be able to move. Then we looked at here the original cos curve, which again is in purple. Just be careful. So starting at 1, going down to 0 to negative 1, 0, and back up to 1 as one full cycle there. And we learned that the derivative of that would be the negative sine curve, negative sine of x, which again here is starting at 0 but going down, coming back up to 0, coming up and going back down would be one full cycle. And that's a reflection in the x-axis of what the actual sine curve looks like, right? Normal sine starts at 0 and goes up, goes to 0, goes down, and goes to 0. So let's look at some more derivative rules. So the derivative rules apply to sinusoidal functions as well. So if f of x and g of x can be, if I can get the derivative of them, if they're differentiable functions, and we'll just say c is a constant if it's a number. So the constant rule, we won't have an actual example of this, but if I just had a number, y equals a number sitting there on its own, then the derivative of that would be 0, which is what we've done so far, right? The constant multiple rule is if I had a function, y equals c multiplied by g of x, so g of x is a sinusoidal function, a wave curve, so sine or cosine curve. Then to get the derivative of that, I would leave the constant the same, I keep it, and just do the derivative of the sinusoidal function, okay? And then we have the sum and difference rule. So that's the only 3 we're going to be looking at for today, and then we'll add on more derivative rules for the next lesson, 4.3. So let's get these 3 under wraps, basically the 2 under wraps for now. If I have y equaling one sinusoidal function and then plus or minus another separate function, then to do the derivative of that, pretty easy. I actually just get the derivative of the one and separated by the derivative of the other, and then just keep it as adding or subtracting, whatever it was originally, just get the derivatives of each. So let's do some examples of this down below here. So find the derivative. I'm just going to get rid of that because it's finding the derivative of, let's just stay with number 1 right now, those 6. So I have y equals the original function is negative sine of x. So that would be, to help you write this out, this is just my kind of hint or suggestion for you, is you could change that to, this is a constant in front, right? Negative 1 multiplied by, this is your sinusoidal function. So if it looks like that, that might help you to understand that that's the constant multiple rule, because there's a constant. And so to get the derivative of that, right, I leave the constant the way it is, so negative or negative 1, and I just get the derivative of the function. So the derivative of sine is cos, and then you can simply rewrite that. So the derivative would be negative, maybe you don't want the 1 there, negative cos of x. Okay, so reflection in the x-axis of the original cos curve is what the derivative would look like of the negative sine of x function. If I go over here to the right b, y equals negative cos of x at first. So again, what I want to do is just acknowledge that there's a constant out in front and that this is my actual sinusoidal wave curve function is cos of x. Then to get the derivative of that, or if you wanted to change your color when you're doing the derivative, would be the negative, what is the derivative of cos? Be careful. It's negative sine of x. So I have a double negative there, like -1 multiplied in. So my derivative would be just positive, the regular sine of x curve. Okay, what if I have f of x, the function is equal to pi times cos of x? I'm not doing the derivative right away. I'm just putting equals and just rewriting it. So visually, I think for some of you, it might help you. Now, pi here is a constant. So I have a constant multiplied by my function, my curve is cos of x. So I have the constant multiple rule. Now, when I'm getting the derivative, right, make sure to put f prime of x. And so I keep the constant the way it is, and I get the derivative of cos. The derivative of cos is negative sine. You hopefully probably have those memorized by now. So just to clean that up, I would write the negative pi sine x. Okay. For d over here, I have g of x is equal to 1/2 of the sine of x function. So again, I'm not getting the derivative yet. I'm just separating out that I have a constant of 1/2 and that my sinusoidal function is the sine of x curve. So now if I get the derivative of that, it's to leave the constant the same and just write out what the derivative is of sine. The derivative of sine is cos. So in this case, I'm not even going to put brackets because it's going to look the same if I were to rewrite it again. I'm just going to write 1/2 cos of x, right? In this case here, it might help to put the bracket because then when you're rewriting it with the negative. So 2 more here for practice. If you look here, this one's slightly different. I have y equals 1/3 pi or pi over 3 sine of x, one term, minus 2 cos of x, a second term. So I have 2 terms with a negative between them. So I have a couple terms. So this is the difference rule, the sum or difference rule, but this is difference because it's subtracting, right? So the rule is just to get the derivative of the first and the derivative of the second. That's literally all we are doing. So if I wanted to rewrite it just to show that there's constants, you might not need to for this one, but hey, until you know that you're understanding everything fully, it's not going to hurt you in any way, right? Then to get the derivative of the first is simply to write down the constant and do the derivative of sine of x, which is cos of x, and then write down the constant minus 2, and then do the derivative of cos of x, which is negative sine of x, which means I have to do some cleaning up here, distributive property. So then the derivative would be the first term stays the same, the 1/3 cos of x. So pi over 3 cos of x, or 1/3 pi. I think I said 1/3 only, but the pi over 3 cos of x, and then positive now, right, 2 sine of x. And that's all there is to it. Just getting the derivative of the first, be careful, the derivative of the second, make sure you've got your rules straight on how to do them to know that you're doing it properly step by step. So you might just have to slow down at first until you're remembering what those rules are. And for the last one, I have 3 terms here actually. So I have pi cos of x, so a constant times cos of x plus 2 pi, the whole thing there is a constant in the middle. So if you wanted to write that out, that's a constant. And then 2 pi sine of x. So 2 pi is a constant times the function sine of x. So again, just to maybe, since there's, if you want to say there's a lot going on here, let's separate. So I've got my constant times cos of x plus that constant, 2 pi is just going to stay 2 pi. There's nothing to separate. Plus 2 pi is my constant, bracket, my function is sine of x. So there's my functions, sinusoidal functions in brackets. So to do the derivative of this, I have a constant, I need to do the constant multiple rule. So the constant multiple rule is to keep the constant the same, the pi, and the derivative of cos, again, is negative sine of x. The derivative of a constant, we looked at that c, right, is like 0, it's gone. Well, I can write 0 in there for now. And then keep the 2 pi, this constant part, and then get the derivative of sine of x, which is cos of x, and then clean that up. So I would have negative pi sine x, get rid of the plus 0. So then I go to 2 pi cos of x. And there we go. So for now, that's going to be the most difficult one that we do in this video. Okay, let's look at some further examples of where we can use the derivative in more of a word problem. So to move this up here, I'm hoping I can fit everything in there, but we'll see. Find the slope of the graph of y equals 2 cos of theta, or 2 cos of x, same thing, evaluating it at where theta is equal to pi over 6. So again, when I said to have the 4.1 video or note out, the reason for that is if you go and look at the 4.1, the cos curve, right? Your cos curve, or just either graph, I guess, if you're looking at your x values, your radian values, you don't actually see pi over 6 on there. But I would know that pi is 180. So I could just take 180 divided by 6, right, which is 30 degrees. We'll write all this down, but I'm just saying to start with, I have this cos function, right, multiply by 2 in front, makes it vertically stretched by 2, and I'm just going to an x value of 30 degrees, and I'm figuring out what the slope of the tangent would be only. Okay, so to get the slope again, at a particular point, I need to get the instantaneous rate of change, which means I just want to get the derivative of this function and evaluate at that x value. So what is my original function? Just to write out from, there's not a lot going on there, but just to pick that out, my original here, sorry to write down, is y equals 2 cos theta. If that really throws you off, you could always change it to an x and change it back to theta at the end. But you probably should get used to writing it out, right, for university. So that is so this is set up as a constant multiple, right? So if you wanted to write that out as a 2 multiplied by cos of theta, so then the derivative of that would be keep the constant, and the derivative of cos is negative sine of theta, and then just rewrite that. So my derivative function is negative 2, put the negative in front, sine of theta. And now we want to, just to write that out, evaluate. Now that we've done our derivative and gone as far as we can, we want to evaluate when we're used to x, but when theta, same thing, is at pi over 6, or we just talked about that's 180 over 6 at 30 degrees, okay? So what we're really figuring out here is the derivative equals negative 2 times the sine of 30, well, I'll just write it out here. So that another way to look at it is negative 2 multiplied by the sine of 30 degrees. So to figure out the sine of 30 degrees, we're looking at special triangles here, right? So special triangles have the pi over 6 in it, or the degrees. I'll write out both triangles here just to show you. So so special triangles have 30 degrees, should be an alert, 45 degrees, and 60 degrees, right? So again, I'm not going to use, I don't think, just looking at, where's my shapes, draw, there's no triangle there, no. You can see that there. So I'm just going to do, because I know I'm not the greatest at drawing things. This is 90 degrees. This might be coming back to you from grade 11. And then we have, I'm trying to draw, and there's pi over 6, okay? And then this one is pi over 3. And then we have 1, the square root of 3, and our hypotenuse is 2. And that's equivalent to, all I'm doing is redrawing the exact same triangle. Again, it's not supposed to look different, just changing those to degrees. So it's still square root of 3, 2, and 1 is not changing, and it's still 90 degrees. But again, pi over 6, we already said here, is 30 degrees. And in the upper corner, pi over 3, or 180 divided by 3, would be 60 degrees. And again, all three of those would add up to 180, just to double check. So there's my special triangle to figure out what sine of 30 degrees is. So again, if I'm standing in this 30-degree angle, or if you didn't change it to 30 degrees and you left it as pi over 6, you'd stand in this angle. Either way, the sine, right? So katoa is opposite over hypotenuse. I'm just going to write it out like that. So then the sine of 30 degrees would be, what's opposite to me? 1 over 2. So that's the value. Sine at 30 degrees is equal to 1 over 2. So I go back and plug that in here. So in the derivative, I have -2 multiplied by, what is the sine of 30? 1/2. Should have kind of extended my bracket there, which is just equal to -2 over 2, right? Which is equal to -1. So that's my derivative. So again, when I differentiate and get my derivative function and I place the x value, in this case theta equaling that value, my answer here is the slope of the tangent. So again, my slope of the tangent is equal to -1. So go back, what did the question ask me? Find the slope looking at this curve, y equals 2 cos of theta, add a value of theta equals 30 degrees or pi over 6. And so I did find the slope. Therefore, the slope is -1. I'm just seeing if there's anything else I need to write down here that I have for notes as reminders for make sure you're in degree mode on your calculator when you're calculating these things. Make sure you're in degree mode when we're looking at special triangles and these sinusoidal functions. And I think that is it. So let's look at one last example here for the video. New example that's still going to draw on the same thing from 2, but extend it. So I need to figure out my slope, but once I have my slope, I'm going to find the entire equation of the tangent line. Find the equation of the line that is tangent to this function, y equals -4 sine of x, add a value of x equaling pi over 4. So again, if you know that pi is 180, 180 divided by 4, you know, you're figuring out at a degree value on x at 45 degrees. So let's do the same thing that we did before. Let's write out what our function is out of this sentence. Write that out first. I'll do over here, y equals, my function is -4 sine of x. So again, you don't really need to know this, but just in your head, you're looking at the sine curve reflected over the x-axis and vertically stretched by 4, right? Instead of going up to 1, it's going to be going up to 4 and -4 there. And we're looking at a value of 45 degrees. What is happening? What is the equation of the tangent line? Is it going to be a positive slope, negative slope, zero slope? What's happening at that value? So to find the equation of the tangent line means I need the derivative to figure out the slope of the tangent. So basically what we're doing is getting the derivative. So again, I'm not getting the derivative yet. I'm just, if I wanted to separate this, right, with the constant and my function. So I have a constant multiple rule. So then my derivative here is to keep the constant and do the derivative of sine of x, which is simply cos of x. So my derivative function is -4 cos of x. And then I want to evaluate that at my x value of pi over 4, which is, if you want to, right, 180 over 4, which is 45 degrees. Which again, maybe this is your alert, pi over 4, you have memorized that that's a special triangle, or if you needed to convert it to degrees, then when you see 45 degrees, you know that this is a special triangle angle. So let's write out our special triangles, just seeing if I can fit it. Yeah, up here, just to not take up some space. So again, there's 2 different special triangles we learned in grade 11. They both have 90 degrees. This one has 1 and 1 on the sides and the square root of 2 as the hypotenuse. And this is an isosceles triangle with pi divided by 4 and pi divided by 4 in the other corners, which is equivalent to the same thing as, I'm just writing it out, but with degrees instead. Again, 1, 1, square root of 2, draw it probably better than I would. So here's my 90. Again, we already did pi over 4, 180 divided is 45 in this corner and 45 degrees in this corner, which makes it isosceles that these 2 sides are equal, which means these 2 angles are equal, right? So again, I'm looking at, I'm evaluating at cos of x. Don't accidentally go back to your original, right? I'm evaluating the derivative when I sub in that x value. So I'm looking at the cos. So I just need to, so that would be the same thing as just writing out here the derivative of -4 multiplied by cos at pi over 4. Or the derivative of -4 times the cos of 45 degrees. So what is the cos of 45 degrees? So again, cos, we don't have we do have x here, not theta. So cos of x is equal to just SOHCAHTOA, meaning adjacent, right? Ka over hypotenuse. So if I am at 45 degrees here, my adjacent to me is 1, and my hypotenuse is, if you can see this, 1 over square root of 2, but I will rewrite that in a different color here. So then I just plug that into my equation. So if I go back to the derivative is -4, and then the cos of pi over 4, or the cos of 45 degrees, is 1 over square root of 2 from my special triangle. That's just going to equal -4 over the square root of 2, right? So -4 over the square root of 2 is my slope of the tangent. That's my slope. I need to find the slope in order, but now to go farther. This would have been the end of question 2, but now I need to use the slope to get my equation. When I'm getting my equation, just to kind of help set you up, we don't want a radical in the denominator. So what I want to do is just rationalize this so that I don't have a radical in the denominator. So what you want to do is, too bad this one is in the way. I'm just going to erase this and write it out this way, that is my slope of the tangent. So to rationalize just means to multiply by the square root of 2 on the top and the square root of 2 on the bottom. Multiply by whatever the radical is on the bottom, because multiplying it by itself is just going to give you a 2, right? And get rid of the radical. And then on top would be -4 square root 2 multiplied together. But I can condense this a little bit, because these are whole. -4 divided by 2 is -2. So it just turns into a nice -2 root 2. So -2 root 2 is also my slope of the tangent. I didn't do anything different here. This is equivalent to this here, right? All I did was rationalize just to not have a radical on the denominator. So that's my slope. Now that I have my slope, I need to get my equation. I don't know how much room I have here. I'm just debating. I guess I'll do what I can. So again, my equation of a tangent line, of a straight line, is y equals mx plus b. So what I have so far is -2 root 2, right? M, subbing it in. -2 root 2, which is slope, which is going in my place of m. Do I have x? Yeah, x was, remember, pi over 4. Multiplied by pi over 4 plus b. So that's what I have going on so far. I need to solve for my y-intercept, my b value. I can't have two variables and solve, so I need to plug in a value for y. And I can figure out my y value, right? Here I have an x value of pi over 4. If I sub this x value of pi over 4 into the original equation, which if you look, I haven't done that. I've only done it into the derivative. Just plug in the value of x there, and then I would get what my original y value would be to put in here. So I think I'm going to clear and start over here, and I'll just rewrite that for you. So we had, where were we here? We had our equation for y equals mx plus b. We don't know what y is. The slope is -2 root 2 multiplied by my x value of pi over 4 plus b. So just here to solve for y, getting ahead of myself, to solve for y, sub x equals pi over 4 into the original equation. So y equals -4 sine of x. I'm just going to go ahead and change that to pi over 4, which equals -4. Did we figure out the sine of pi over 4? I think we just figured out the cos of it. So if we were to go back and look at that special triangle, if you were to be standing in, again, 45 degrees, and sine is opposite over hypotenuse, you would still have 1 over the square root of 2. So I would have the sine of 45 degrees is still 1 over the square root of 2. Just go back and look at your special triangle, and if you have questions, let me know, which again is negative 4 over square root of 2, but we don't like a radical, so let's rationalize, which is just going to equal negative 4 root 2 over 2, which again is the exact same thing as before, just negative 2 root 2. And it's not always going to be that it's the same, but this is my y value now. Be careful. I'm subbing this in. This is my y. So let's go back up to my straight line equation of the tangent, which is y equals mx plus b. So that's going to give me now y on the left side is now negative 2 root 2 equals, okay? And then the right side, negative 2 root 2. I know it looks a little weird. It is getting busy here. So this is where you slow down to make sure that you don't make any mistakes. So now the next thing I'm going to do is simply multiply across here. So I have negative 2 root 2 pi over 4 plus b, right? And then I can see that I have 2 and 4. I could change that 2 quarters, right? Lowest terms to 1/2. So there would be a 1 there and there'd be a 2 just to kind of condense it. So I had to have negative 2 root 2 equals negative root 2 pi over 2 plus b. Yes, it does look kind of ugly. Negative root 2 pi over 2. And then I'm just stopping 2 and making sure that I'm not making any mistakes. So now what do I want to do? Can I condense this whole b value here? What if I took this, obviously, if it was just a constant, which it is, and bring it over onto the other side, right? Then I would add. So here I would have negative 2 root 2 stays the same, and then I'm adding root 2 pi over 2 equals b. So then let's get a common denominator. Just call it an LCD, will be 2, right? That's over 1. So if I was to, hopefully you see this, multiply by 2 and multiply by 2, how would that change things? If I'm multiplying by 2, that's going to be negative 4 root 2 over 2, right? Well, let's write that out so we don't go too fast. Negative 4 root 2 over 2 plus, this doesn't change because 2 is already in the denominator, square root of 2 pi over 2 equals b. But then I don't want to condense this down to negative 2 root 2 because then I don't have that common denominator. So now I'm just putting it together. B is going to equal, I didn't do anything other than just putting b on the left-hand side, so you don't have to do that. You can write out negative 4 root 2 over 2 plus root 2 pi, sorry, and that's all over 2, so I should probably just move this over just to look like it's more centered. And I could have had equals b, right, on the right-hand side. So I have my b value, I have my m value. Now I'm just going in and subbing it into my equation, y equals mx plus b. Instead of squishing it, I'm just going to clear, okay? So again, what I'm looking at is y equals mx plus b, just to finish this off. I know my slope, let's say, is negative 2 root 2. I know my b value is, I'm just going to go back here. The last thing I wrote down was negative 4 root 2 plus root 2 pi all over 2, that big mess. So to plug that in, again, whenever you're plugging into a straight line equation, you want x and y to remain variables, and you're just plugging in values for m and b. So I have here, my slope is negative 2 root 2 x plus, but my b is negative, so plus bracket negative 4 root 2 plus root 2 pi over 2. And I could just leave it like that, honestly. If I wanted to, I could change it to negative 2 root 2x. So y equals mx, negative 2 root 2x. And just if I were to distribute these, the positive 1, right, I'd have a negative here and then a positive here. So I'd have a negative and then a positive. Normally you might want to write the positive first. So then I'd have the positive square root of 2 pi, and then this would end up being negative 4 root 2 all over 2. But you, like I said, you could have just left it the way it was before. I'm not sure. Again, if you take a look, the textbook might have written it this way. If you have something slightly different, the textbook, just go back to your previous step and see if they might have left it like that. Okay, so let's give these a try.